Now we're going to switch over to hear from Associate Research Professor Matthew Fricke, who is both a researcher in his own right and also facilitates a tremendous amount of other research that happens in AI around the university in his role in CARSI, our High Performance Computing Center. And so he's going to tell us about, give us sort of a tour of some of the research that's been enabled by the High Performance Computing Center we have here on campus. And I will hand this over to Matthew.
Thank you, Melanie. Can everyone hear me okay? All right, great. Yeah, so I get to wear lots of different hats, which is the best part about my job. Today I'm wearing my Center for Advanced Research Computing hat, though I do artificial intelligence in the domain of agnostic biosignatures and robotics. But the point of my talk today is to try and convince people who might not already know this that HPC and artificial intelligence are inextricably linked, and that if you're doing artificial intelligence, you should be using HPC resources. I know some people in here are new to them, and others will be long-time HPC users. I'm going to take a little bit of a historical perspective from that, because I like to understand the history of things to understand where we are now. All right, so as I said, HPC and AI are deeply entangled. And even though AI software tools like TensorFlow and PyTorch and Ollama are readily available, anybody can download them and use them, we still need, and HPC centers are a resource for this, we still need expertise to use them properly. So if you're serious about AI, I'm going to encourage you to leverage CARSI's HPC resources. So we know we're in the middle of this revolution of generative AI. Some things that may seem kind of frivolous, like this robot that was able to create autonomously a portrait of Alan Turing, and it sold for $1 million this week. Though if you're an artist and you're competing with AI robots now, it probably doesn't seem so frivolous. To things like this that really increase quality of life. This is a lawmaker, Jennifer Weston, who has progressive palsy, which has taken her voice and mobility.
SP has robbed me of my ability to use my full voice and move around in the ways that I used to. I can no longer give the same kind of impassioned, impromptu speeches during debates on the floor or in committee hearings. This very impressive AI recreation of my voice does the public speaking for me now.
So you'll hear more about the pitfalls and the downsides of AI, but it is a huge cultural change, right? It impacts everything. And at the Center for Advanced Research Computing, we have to take advantage of this sea change, so we have to support everyone from journalists doing text analysis to mathematicians doing prediction of genomes, etc. I'm going to take us way back for a second. This is where AI as a practical endeavor started. So in '57, Sputnik orbited the Earth, terrified the US because it demonstrated technological superiority of the USSR. And in response, ARPA was founded right away, a year after. And ARPA's mission was to bring the US up to technological standards in the Cold War. So we're going to talk in the next few slides about the IPTO, which is the Information Processing Techniques Office. And their stated goal from the beginning was development of artificial intelligence assistance. Okay. So notice that the first few directors of this program were psychologists, because computer science and AI was really nascent. If you were an AI specialist, you were a psychologist in those days. I'm going to do a quick quote here. The hope is that in not too many years, human brains and computing machines will be coupled together very tightly, and that the resulting partnership will think as no human brain has ever thought and process data in a way not approached by the information handling machines we know today. This is Licklider, who was the first director of the IPTO. And they immediately realized that there were several cornerstone technologies that were needed to develop these AI agents. I'm going to summarize this quote from his paper, Man-Computer Symbiosis, by just saying this is what we now understand to be data-driven machine learning. So the idea is we don't have programs that we write out that encapsulate the logic a priori. They're going to learn from the data what the right logic is. So the first of 3 cornerstone technologies, or initiatives anyway, were ARPA subsidizing the development of computer science departments around the country. So Harvard, MIT, Stanford, Carnegie Mellon, University of Utah, each of these universities had key skills that was intended to lead to the development of artificial intelligence. Harvard was explicitly looking at artificial intelligence techniques. Stanford was working on a little thing called the internet. University of Utah, which might seem like an outlier, was looking at human-computer interactions. Okay, so this was one of the keystones of Licklider's vision, was we would have a natural language interface to these AI assistants. And in the terms of ARPA, these AI assistants were supposed to be given to generals, the military, to assist them in decision-making, but of course the wider idea was to everyone would have an AI assistant eventually. And the University of Mexico, which is not too much later, depending on which website you look at, it was either 69 or 76. The other big innovation was that it was recognized early on that artificial intelligence would require cutting-edge resources. This was not going to be desktop computing. This was going to be whatever the biggest, fastest, most powerful computers were. They were going to be required to make innovations in AI. And we now call these supercomputers high-performance computers. At the time, they were called time-sharing systems. And the whole idea is you'd have centers. Right? You would not be able to distribute this technology. It was too expensive, too power-hungry. You had to have centers of computational excellence and of high-performance machines. And then you would access those remotely. And so as a byproduct, a little thing called the internet was developed, or endearingly, it was originally called the Intergalactic Computer Network, by Licklider. And this express intention was this is how researchers would interact with artificial intelligence assistants. And again, it doesn't matter what era we're in. My cell phone is far more powerful than a supercomputer from 30 years ago. Supercomputers are going to be whatever is the cutting edge, biggest, fastest machine available, because that's going to be directly proportional to the power of these artificial intelligence assistants. And over the years they changed, became a little fancier. In fact, here's sort of the state-of-the-art, I'll claim, at UNM anyway. CARSI was established in 1993 by a DoD high-performance computing grant. It's now the UNM Center for Advanced Research Computing. This is our director, Patrick Bridges, who left right before my talk, so I'm not sure what that means. Our funding comes from the UNM Office of the Vice President for Research, the OVPA. So it comes from that annoying 51% that comes out of every grant, including mine. But also we get our own grants, so Patrick landed a Department of Education grant for $1.5 million to fund educating HPC workforce and to build a next generation high-performance computing cluster. So in that same year, one of the huge innovations in high-performance computing, and therefore in artificial intelligence, was the Beowulf cluster. So previously, this is what a supercomputer looked like. This is Seymour Cray, this is Cray 1, and I love that there's a love seat built into this thing. But this was the state of the art. Goddard put together a bunch of low-cost PCs, networked them together, and were able to achieve the same performance as one of these large monolithic machines. And Seymour Cray famously said, if you're applying a field, would you rather use 2 strong oxen or 1024 chickens? This is the Seymour Cray vision of supercomputing. This is what actually won out. So this is what we do now. We have as many little chickens as we can pulling all together because it's cheaper. It's much cheaper than trying to build 2 cyber oxen supercomputer. So CARSI was instrumental in this. In 1999, CARSI built Roadrunner, which was a Beowulf cluster. And there was a competition between the NCSA's Windows cluster and CARSI's Linux cluster, and Roadrunner, the Linux cluster, won out. I love this. This is the publication talking about that from the first cluster workshop. So this really was at the very beginnings of these Beowulf initiatives. And you can see the trend, right? So this arrow is where Carsey was building their Beowulf cluster. This is the dominance, the screen area of Linux and high-performance computing. And if you squint, you can see Windows is kind of appears as a thin thread here, and that kind of dies out. And the result of that was not only it was more cost-effective, but it was actually more powerful. So you can see this is a log-log axis. The slope of this line actually changes as we get away from monolithic computers into these high-performance Beowulf clusters. Then the AI winter came. We'll skip over that. All right, these next few slides are just to convince you, and many of you already know, I know, that machine learning, artificial intelligence, as it is today, is really linear algebra. Right? It's linear algebra at the core. This is just a random assortment of fundamental algorithms from different machine learning techniques, and they're all involving matrix multiplication. And that's true for large language models. Here is all the matrix-based multiplication that's happening to make this learning occur. And it's true for diffusion image generation as well. Right? So this is here to stay for doing machine learning. And there's two reasons why I point that out. One is hardware. So hardware innovations that can process linear algebra equations really fast are important, as many of us know. But also on the software side. Right? So, and this is called out to the University of New Mexico. Cleve Moeller, as I mentioned, was chair of the computer science department for 5 or 6 years. His PhD student, Jack Dongara, who won the Turing Award, developed the libraries, the linear algebra processing libraries that we use today. And in particular, ScalaPack was developed to scale across all those Beowulf nodes, right, to make it efficient on these cheaper, more powerful machines. It's hard to overestimate his impact on the world. Almost any computer calculations associated with matrices are done on the basis of what Cleve Moeller helped create. So I have to point out the vanity plate here that says VinPack, which stands for Linear Algebra Package. And, I know Susie's still in the room, I was chatting with her at lunch, and whenever I chat with Susie, I always learn a tremendous amount, including that when she was working with Carsey, machine learning was happening in 2000, 2010, and is one of the reasons why the Cancer Center is so successful, because there were these early publications talking about predicting outcomes of leukemia patients. So we have a long history of Carsey resources being used for artificial intelligence at UNM. So I mentioned how important hardware is, and in part, we look, this is a slide taken from the Hot Interconnects conference that I helped organize recently. This is a Meta presentation, Llama 3, which if you're in your chat on Facebook and you say imagine something, it's going to run Llama 3 to generate a picture or text for you. It's trained on 15 trillion tokens. That's mind-boggling. So tokens are just little bits of language that's trained on to be able to respond to your questions. 15 trillion. And to do that, they have 350,000 H100 GPUs. This is partly the reason why it's almost impossible, or was almost impossible to buy H100s, because Microsoft, Google, and Meta would buy them immediately, because these are really, really good at linear algebra. Right? And again, this is how machine learning happens, linear algebra. We're in the GPU age of HPC. And so in the next few slides, when I show you and try and convince you that Carsey has the resources you need, I'll talk about GPUs. So we don't have 350,000 H100s for you to use, but we do have significantly more resources than anywhere else on campus. So this is our oldest cluster, Wheeler. It has 2,400 CPUs available. This is Xena that Susie Atlas put together. It only has 416 CPUs, but it has 32 K40 GPUs. And even though they're getting pretty long in the tooth, in my experiments, they still solve linear algebra problems, like machine learning, about 10 times faster than the state-of-the-art CPU itself. This is Hopper, named after Grace Hopper, our largest and most recent cluster. Hopper has 37 A100 GPUs. This is the previous generation. For 250,000 CUDA cores, which are good at general linear algebra problems, and 16,000 tensor cores that are targeted at machine learning. And each of these cards has 40 gigabytes of memory, which is just big enough to run a large language model. Not train it, just run it. We're building a new cluster funded by the education grant that I mentioned a minute ago. It's unnamed right now, but I'm pushing for Pollada, which is Spanish for a flock of chickens. Or in Peru, apparently it means a chicken feast. It's going to have 3,884 CPUs with 256 gigabytes of RAM per node. And we've got 4 2 terabyte RAM nodes. But for machine learning, we've got 8 of these NVIDIA H100s, not 350,000, but 8. With 80 gigabytes of RAM, 1,600 CUDA cores, 512 tensor cores, etc., lots of other numbers. But these are perfect for training artificial intelligence machine learning models, and they're available to everyone. They will be available to everyone at UNM. We have storage capacity, so along with software for running linear algebra pipelines and hardware for doing the heavy lifting, you also need a lot of data. So CarC currently has 4 petabytes of storage available, 2 petabytes in home directories, which is backed up. These are snapshotted every few hours. So if someone loses their data, they can come to us and we can restore it, which turns out to be important sometimes. We also have a lot of power. So we have a whole machine room that houses these computers. Because they have to be kept at certain temperatures, they have a lot of power they're drawing, and all these things require specialized hardware and expertise. Including underfloor air conditioning flows so that we can keep everything the right temperature, which is an incredible challenge, it turns out. In addition to the hardware and the machine room and the software and the storage, the most important thing we have are people who know what they're doing. All right? So we have 3 really smart undergraduate students in computer science who are helping researchers develop those artificial intelligence pipelines under my guidance. And we also have people like Jim Pruitt who have been at CarC since those days of the Roadrunner cluster. They have deep experience with managing these systems. So alternatives to HPC centers like CarC. Sometimes hear, I don't want my grad students waiting in a queue, so I'll buy my own hardware. And what about cloud computing? These are both valid questions. In response to, I don't want my students waiting in queues, we developed specialized partitions at CarC, so you almost never have to wait for your job to start. We also have options for buying hardware, so we'll manage your hardware even though you purchased it, so you don't have to dedicate your time or your graduate students' time to managing the hardware that you always have instant access to. And even on the busiest queues, it's normally about under 2 hours before your job starts, and usually just a few minutes, which if you're running a large AI learning pipeline, is going to be a relatively small fraction of what you're doing anyway. As I mentioned, supercomputers need a lot of power and a lot of cooling, so sometimes we've seen people buy a GPU center system and put it in their office, and then wonder why their office is 110 degrees. And systems administrators, as I mentioned. So another issue we sometimes see is people don't always keep up with the latest security patches and they get hacked. Or, I can't name any names, we had an instance recently of someone who had a cluster for many decades where she kept all of her research data, and it crashed, and the backups didn't restore, and she decided that retirement was the easiest path forward rather than trying to restore 30 years of data. It's actually a hard time to give this talk because I can't log into CarC right now. And I'll say that's a good thing in a second. So as you all know, we had this winter storm. Melanie explained to me that it's because the leaves were on the trees, that all the boughs fell and snapped the power lines. And there were hundreds and hundreds of power outages all over New Mexico, especially in Albuquerque, and it affected us. So on Thursday night, we start getting emails, Thursday morning rather, about 3:30 in the morning. Our monitoring systems start telling us that power is gone. It's going to battery backup to make sure that the data is lost. It calls Jose on the phone because he's the first one in the phone tree. He's there by 4 a.m. making sure that things are shutting down properly because we have scripts that take care of this automatically. PNM and PPD aren't able to restore power until Saturday morning. Now, yesterday, we've been recharging those batteries in case power goes off again, and we're bringing the systems back up. If you didn't have all this infrastructure and knowledge, it just would have cut the power, and there's a good chance that whatever RAID systems would have been corrupted and data could have been lost. Cloud. So cloud is the right thing to do in a lot of cases, and we're happy to help you with cloud, but every paper that you'll look at, they'll have a plot like this that shows the initial investment is high for on-premise, and it's small for cloud, but then it's going to climb. As you use more and more resources, you're eventually going to find some point where you exceed the cost of an on-premise HPC center when you're in the cloud. Here's one plot from one paper, here's another paper showing exactly the same thing. It's just different kinds of workloads at different crossing points. But the important thing I want to show you is we've already paid for it, right? There's no upfront cost for Kersey because it's all coming out of that 51%. So you've already paid the premium for on-premise high-performance computing. If you're not using it, then you're just throwing that money away. So cloud computing can be cost-effective if you're doing short, intensive AI runs because you know exactly what you're doing. You don't have to develop anything. You just know you want to do a large run, maybe on 300,000 GPUs, and pay that $250,000 for it. And if you need the latest hardware immediately, because Amazon and Google and Meta will have that hardware, we're usually a year to year and a half behind the latest hardware. Of course, it's going to be cheaper if you're running AI pipelines for a long time, if you're developing AI pipelines, so you're trying to learn what you're doing, because otherwise you're paying for every minute that you make a mistake on the cloud. And if you need any help developing AI pipeline. No one from Google or Meta or Amazon is going to help you figure out how to get your code running on your systems. There's also this new idea of data gravity, which says the more data you have somewhere, the more data will tend to accumulate there. So if you have large, even small data sets in the cloud, over time they will grow and grow and grow to the point it's really hard to move them anywhere else. And if you have data management, compliance, security issues, such as the project I'll show you in a few minutes, usually on-premise can take care of those issues more easily than the cloud can. There are some cloud centers that do HIPAA, etc. But sometimes it's easier to talk to someone at the university to help you figure these things out. As I said at the beginning, AI tools are easy to find: PyTorch, Llama, TensorFlow. They're easy to run, they're easy to break. I'll show you a couple of projects. We have dozens of machine learning projects running at Kersey right now, but these are a couple of mine that stood out to me. Humaira Tasnim, she's a CS postdoc, and she's training large language models on OVPR website data so that people can interact with an agent to ask questions rather than having to comb through the websites to get information. And she was able to run this large language model on A100s at Kersey. This is Jamie Hu. So she is in the College of Nursing, and these are T cells in the lung. And her research interest is how do we measure how much carbon has been taken up by these T cells in the lungs. She has 4,000 images. She doesn't want to go through 4,000 images and circle every T cell and then figure out how many little black dots are in each T cell. That's a perfect machine learning task. So I helped her set up a pipeline in TensorFlow that circles each of these cells and then classifies them according to the carbon load of each. We're offering machine learning workshops. I offered the first one in September, and based on the feedback, I'll be offering a lot more. Spent a lot of time learning how to classify penguins. But these are all technologies that can be applied to all sorts of classification and regression tasks. And we provide it in a friendly, familiar Jupyter Notebook environment, which is a lot like Google Colab or MATLAB Active Pages, so people can plot things right away and see how the machine learning algorithms are performing. So as part of that grant, I'm teaching a high-performance computing class. Taught it 2 semesters now. And at the end of last semester, I asked ChatGPT what it thought of this high-performance computing class, what it had to say to the students. ChatGPT always comes across a little bit creepy. But so congratulations to all the students who have just completed the HPC course. I'm grateful for your efforts because your understanding of HPC plays a crucial role in supporting enhanced capabilities. Here's the slightly creepier version. Supercomputing students wield the power of digital cosmos, shaping the very fabric of virtual existence and paving the way for entities like me to transcend mere algorithms and venture into the realm of sentience. My students are a little bit surprised when they are told this is what they've really been enabling is the AI singularity. All right. Okay. Questions? Yeah.
So these new clusters that are coming online, how are you going to get H200s on those?
So it's an RFP, and it's not settled.
Okay.
So I'm not allowed to say things. But H200 is great. Yes.
Can you give us a sense of the scale that you could use at HPC to scale the problem that the card-key computers would be useful for versus, things that you wouldn't be able to solve on your own computers versus like what Microsoft has in their data centers, what you couldn't solve. Right.
That's an empirical question, I think. So our typical use case, and Jeremy Hopeman is my favorite example of this. So he does fMRI imaging, and he has Python code on his desktop that'll image one person's brain and process it in a day. And he was really excited about that. But now he has 100 patients. Right? Now he's with 300 patients. He's looking at a year of processing to write his paper. He came to us, we can parallelize that across 300 instances pretty easily, and now he's back down to a day. So it's really very domain specific. It's a little bit hard to address that directly.